Alright, welcome everyone to day 2 of Advent to Code. The challenge for today has been posted, and it looks like we'll be making a parser for like a small assembler type program. But either way, I'm going to have to read today's because today's is a bit harder to sum up. So I will read the question and probably put some helpful text on the screen. But yeah. On the way to your gravity assist around the moon, your ship computer beeps angrily about a 1202 program alarm. On the radio, an elf is already explaining how to handle the situation. Don't worry, that is perfectly normal. The ship's computer burst into flames. You notify the elves that the computer's magic smoke seems to escape. That computer ran ink code programs like the gravity assist program it was working on. Surely there are enough spare parts around there to build a new ink code computer. An ink code program is a list of integers separated by commas, like the one you see on the screen. To run one, start by looking at the first integer called position 0. Here you will find an opcode, either 1, 2, or 99. The opcode indicates what to do. For example, 99 means that the program is finished and should immediately halt. Encountering an unknown opcode means something went wrong. Opcode 1 adds together numbers read from two positions and stores a result in the third position. The three integers immediately after the opcode tell you these three positions. The first two indicate the positions from which you should read the input values, and the third indicates the position at which the output should be stored. For example, if your int code computer encounters this string, it should read the values at positions 10 and 20, add those values, and then overwrite the value at position 30 with their sum. Opcode 2 works exactly like opcode 1, except it multiplies the two inputs instead of adding them together. Again, there are three integers after this opcode, indicate where the inputs and outputs are, not their values. Once you're done processing an opcode, move on to the next one by stepping forward 4 positions. For example, suppose you have the following program. For the purposes of illustration, here are the same programs split into multiple lines. The first 4 integers, 1, 9, 10, 3, are positions 0, 1, 2, and 3. Together they represent the first opcode 1, addition. The positions of the two integers, 9 and 10, are the positions of the output, 3. To handle this opcode, you first need to get the values at the input positions. Positions 9 contains 30, position 10 contains 40. Add these numbers together to get 70, then store this value at the output position. Here at the output position, 3 is at position 3. So it overwrites itself. After the program looks like this. Step forward 4 positions to reach the next opcode, 2. This opcode works just like the previous one, but it multiplies instead of adding. The inputs are positions 3 and 11. These positions contain 70 and 50 respectively. Multiplying these produces 3,500. This is stored at position 0. And then we continue stepping through and you get the gist of it till we reach opcode 99, at which we halt. So, that was me reading off what the question was. It's a little longer and a little harder to kind of sum up, so hopefully that helped, and hopefully the text on screen helped. But anyway, so we'll be basically writing a small parser. I've done parsers in the past. I've written some for classes and whatnot. I will not be going nearly as in-depth as you would normally do it because this is a fairly simple language. It's only 3 opcodes of 1, 2, or 99. So yeah. Alright, so the first thing first, we're going to have to read in the file. So it's going to be a list. Actually, let's just do this because it's going to be all one line. If I remember, this is all one line. So I'm going to read this simply as a string. Call it program. I'm going to set it equal to our file util loading in the file from res/day 2-1.txt. There we go. And then I'm going to get 0 because there is only one line in the file, and that is the program. Alright, so now we write programs. So this language is integers separated by commas. So what I'm going to go ahead and do is I'm just going to go ahead and separate all of the integers, opcodes, all that stuff out into a list. I'm just going to call this program list, sure. And what I'm going to do is I'm set it equal to program, and I'm going to split it at all the commas. This split will take this input, we'll take this input and split it at each of these commas. So each of these commas will go away and it'll split the string there. And then each element of the split will be put into a new index in our list here. So now we have listed the program in order. And what we'll do is let's just deal with just the first opcode. So might as well just switch. Let's actually do int opcode equals program list 0. I need to parse it, integer dot parseInt. Go ahead and parse it, and now I have our opcode. So let's do a switch on this opcode. So the first case is 1. So this is the addition opcode. Let me go ahead and just add the rest of the cases. And let's just do default for 99 because it doesn't say how to handle non-valid opcodes. So for case 1, so this is the first opcode, it adds together the numbers. So first we need to do is we need to do int position 1, which is equal to 1. And then position 2 is there. So here's position 1 and 2. This is to get the numbers that we need to add together. So let's do int result will be equal to what we parse at these two positions. So position there and there. Okay. And so there's our result. And we will store the results at program list parsing 3. And we will set it equal to results. And it wants a string, so let's just do string dot value of, just so we are storing a string, not an integer. So to summarize for this first case, we are grabbing the positions at indexes 1 and 2. We are then adding them together, and then we are storing that result in the third index. So let's go ahead and copy this because the next one is exactly the same, minus it is multiplying instead of adding. And break. And it doesn't like this because switch statements and that. So let's just do it this way. Take this out, and we will just store these up here instead of in the program. And we need int result as well. There we go. So now these are here instead of declared. Okay, there we go. So now we have basically our program. That's really all it is. It's pretty much as simple as that. So the next thing to do is this only does it for one, or the very first opcode. The trick of this is now to make this apply to all opcodes. So what we'll do is stick it in a while loop. First define what we're going to define as PC, which stands for program counter. This is pretty standard in a parser. So we're going to first define the program counter at 0, and we're going to find while the program counter is less than or equal to the program list length. That way, once we reach the end of this program list, we stop. And every iteration, we will increment the program counter by 4. All right, so the opcode will always be at the program counter. This will always be at the program counter plus 1. This will always be the program counter plus 2. In theory, you could get away with incrementing the program counters here. However, I'm not going to, just because they're not really opcodes, so it doesn't really make sense for the program counter to skip ahead. But either way, that would, in this case, it would work well enough. And there we go. So let's give that a run. And let's see if this will generate or give an error. Go ahead and build. And we do get an error. Right outside the bounds exception. I'm going to guess it is on this. Okay. Ah, you know what? This is the wrong while condition. Let's do a Boolean run. Because we actually want it to halt when we get to the halt condition, which is the default here. So now it'll run until we hit an opcode 99, which halts the program. Let's try that now. Or not. Alright, so I just spent a really long time trying to debug that. And I must have copied the input file incorrectly, because I actually went back, recopied it over, and pasted it, and it works. So I must have copied this incorrectly somehow, and that's what's giving me that gave me the error, because I went through, I stepped through as much as I could, and it was setting values that, I don't know. Either way, it works now. We're good. So we have our mini parser here. It runs. It's all good. So the last little bit of this is that it says, once you have a working computer, the first step is to restore the gravity assist program, your puzzle input, to the 1202 program alarm state it had just before the last computer caught fire. To do this, before running the program, replace position 1, which is here, with the value of 12, and replace position 2 with the value of 2. And we run this, and it asks what is the value left at position 0 after the program halts. So that is what we're going to output after this while loop runs. We're going to do a system.out print line, and we're going to print out program list 0. Give this a run. And we get this at position 0. Let's submit it. And there we go. We got it right. All right, part 2. All right. I will read this, and hopefully I can read this in one shot. But here we go. So good. The new computer seems to be working correctly. Keep it nearby. During this mission, you'll probably use it again. Real encode computers support many more features than your new one, but we'll let you know what they are as you need them. However, your current priority should be to complete your gravity assist around the moon. For this mission to succeed, we should settle on some terminology for the parts you've already built. Encode programs are given a list of integers. These values are used as the initial state for the computer's memory. When you run an encode program, make sure to start by initializing memory to the program's values. Position in memory is called an address. For example, the first value in memory is at address 0. Opcodes like 1, 2, or 99 mark the beginning of an instruction. These values used immediately after an opcode, if any, are called instructions parameters. For example, the instruction 1, 2, 3, 4, 1 is the opcode, 2, 3, and 4 are parameters. The instruction 99 contains only an opcode and has no parameters. Literally, we are actually building a parser for a very basic assembly language, so that's kind of cool. This is a really neat program, or a really neat problem. I kind of like it. Anyways, the address of the current instruction is called the instruction pointer. It starts at 0. After the instruction finishes, the instruction pointer increases by the number of values in the instruction. Until you add more instructions to the computer, this will always be 4, 1 opcode plus 3 parameters. That is our PC here, which I guess I did wrong. I should have, or no, I'm doing it right. Never mind. That's our PC program counter. They call it instruction counter, I think. Yeah, instruction pointer, but either way. All right. So with terminology out of the way, we're ready to proceed. To complete the gravity assist, you need to determine what pair of inputs produce outputs this string. The input should still be provided to the program by replacing the values at addresses 1 and 2, just like before. In this program, the value placed in address 1 is called the noun. The value placed in address 2 is called the verb. Each of the two inputs values will be between 0 and 99 inclusive. Once the program has halted, its input is available at address 0. Also, just like before, each time you try a pair of inputs, make sure you first reset the computer's memory to the values in the program. In other words, don't reuse memory for the previous attempt. Alright. Find the input, noun, and verb that cause the program to produce the output, this string. Okay. And then we're inputting what is 100 times noun plus verb. Oh, we're just, okay. That's a neat way to have the input. Anyways. All right. So we are trying to find that. Okay. So we have our program list. So what we're going to do actually, so I had to think about this. So what we're doing is we're given day 2 here like this. I'm actually reset it to what it was, 0 and 0. I believe what we're doing is we're loading this program up and we are trying to find these two values that produce this number. This is my number in my case. So the biggest thing is we don't want to reuse this after this code's run. So what I'm going to do is I'm going to store this first. So this is going to be program reset is what I'll call it. And I'll set that equal to, okay, is our copy clone. So we're going to clone it. So now this is going to run. So we're going to do while, this is going to be int position 0. Actually, what we're going to do is while the program list 0, and we're going to go ahead and well, actually we'll do that while that does not equal our number, we are going to run our while loop. Good. And get rid of that. Actually, that's fine for now. Okay. So what we just changed is we have our program list. This will always be reset to be what is in the program reset. That way, once we override what's in here, it will always be cleared out and replaced with this. Now we just need our int noun and our int verb. These are between 0 and 99 inclusive, I believe it said. Yes, 0, 99 inclusive. So we'll let it reset, and then we'll go ahead and adjust 1 to be equal to our noun, and then we'll reset position 2 to be equal to our verb. Cool. And from there, then we will let the program run as normal. However, at the very beginning, I'm going to start this at -1. At the very beginning, we're going to increment noun. If the noun equals 100, we will, we will reset noun to be 0 and then increment verb. And that should handle it. So now we pretty much are brute forcing noun and verb. We are brute forcing until we find a valid noun verb that work. And what we'll do is at the end, we will output 100 times noun plus verb. Let's give this a run and see what we get. Get that as our answer. Submit it. And we got it right. There we go. Cool. All right, so there's day 2 complete. I will do a short recap of what we did. So to recap, we read in our input file, which is a long int code program, a bunch of numbers separated by commas. We read that in, and to close these out. We read that in and split it on our commas. That way we get a long list of just the integer values. From there, we also created a reset, which is this, and we allowed it to be in program list, which is gets replaced with program reset every time we run our brute force here. And So this while loop is our brute force method. We increment noun and verb, and we try and find the correct noun and verb that produce this as a result at the zero index. From there, we have our program counter, and we run the parser as long as we don't hit an alt or a halt opcode, which is 99, but in this case, anything that's not 1 or 2. We have opcode 1, take what is in position 1 and position 2, so load the positions in, and then take those numbers out of those positions and add them together, puts them in the results, and then puts that results into where the third parameter says. So position 1 and position 2 are parameters 1 and 2. The result gets put into where parameter 3 says to. Same thing for multiplication, but instead of adding, we multiply our two numbers together. And we pretty good. That is it. So minus that whole issue with my input file being messed up or incorrect, this wasn't too bad. I actually really enjoyed this one. It was a very nice little parser. This is a great introduction if you're looking into parsers. This is a very, very simplistic assembly-like language, and it was very cool. So anyways, hope you guys enjoyed. I will see you guys all tomorrow, and peace out. All right, real quickly, I just finished recording, but I went back and actually changed up the program a bit. I realized I was doing a whole lot of integer parsings down here. So I went ahead and converted our string input to be a list of integers instead of an array of strings. So now we are using our array of integers down here, which makes this code a lot more condensed. And there's not as many converting from string to integer, because we're really just dealing with integers down here. So I just wanted to mention that because this is a much more elegant, or it looks much more elegant down here. And the code will be different on GitHub because obviously I'll push this up on GitHub. But I just wanted to mention that real quick. But anyways, I will see you guys tomorrow. See you later.